Test 2, a commentary. You guys did great on this test, so hooray for that. Number 7, two objects are dropped from rest at the same height. Object A falls through a distance dA during time t. Object B falls through a distance dB during time 2t. If air resistance is negligible, what is the relationship between dA and dB? I'm going to need a diagram, and I'm going to need an equation. We call this the second kinematic equation, and we said that the initial velocity is 0, so there you have it. Distance fallen is proportional to time squared, and since one of them fell for twice the time as the other, dA is equal to 1/4 dB. Now, as a couple people had answered D. I get confused about this all the time. Is dA equal to 1/4 dB, or is dA equal to 4 dB? That can be tricky for guys like me, people like me, so I'd say draw a diagram. Number 11. 3 blocks A, B, and C of masses 1, 2, and 3 kilograms respectively. Their respective blocks are initially at rest on a frictionless surface as indicated in the figure above. What force F has to be applied on block C in order to accelerate this family to 2 meters per second squared? And I'm going to draw a box like that. I'm going to shade it in. That's a 6 kilogram family, so F equals ma. That's the equation. You got 6 kilograms at 2 meters per second squared. You're talking about a 12 Newton force. And I was a little disappointed when I read this problem because I'm like, I love this problem. I used to hate these problems, but now I like these problems. I want to go a little bit off script here. We're going off script and we're answering a different question. So red alert, different question. Ignore this if you want to. My one question is, what is the force of block C on block B? What is the force of block C on block B right there? And it's the same acceleration, but this time you got a different mass, the 2 meters per second squared on a total combined mass of 3 kilograms. That would be a 6 Newton force of block C on block B, which is not, I repeat, not the question there. Now that I've made things more difficult than they needed to be, on to question 12. An electric motor provides 0.5 watts of mechanical power. How much time will it take this motor to lift a 0.1 kilogram mass at constant speed from the floor to a shelf 2 meters above the floor? We've got all sorts of quantities here, 3 different quantities. And the reason I'm doing this problem is because I don't like these questions, and I don't think we did a lot of them in class. They're the P equals FV type questions, and the key phrase is constant speed. Key phrase is constant speed. That means by definition acceleration is 0, net force is 0. Net force is 0. We need to figure out the forces on this 0.1 kilogram mass. Weight is equal to mg. I looked, that equation was not, I'm going to put it there, but not on the extra equation sheet. It's such a friendly equation, especially when you use 10 meters per second squared as an approximation for g. We have a 1 Newton downward gravitational force, a 1 Newton upward pulling force that's pulling this thing upward at constant speed, and there you go. Power is equal to force times velocity. Velocity, don't you know, is distance divided by time. The answer is E. Next one, number 18. Identical net forces, aren't they cute? Act for the same length of time on 2 different spherical masses. Which of the following describes the change in linear momentum? A momentum problem of the smaller mass compared to the larger mass. A momentum problem, a momentum equation. J equals integral F dt equals change in momentum. Let's simplify that maybe a little bit. I feel okay simplifying it because the forces, they're the same. Times, they're the same. We've got one mass is smaller, and that means delta P is the same. That means delta P is the same. See, a couple of people answered B, but B's not correct. C is correct. The change in momentum is the same. It's true that the smaller mass thing travels at a bigger velocity, and the bigger velocity thing goes at a smaller. Well, that's not what they're asking. That's not what they're asking. But I don't like this question because they mention spheres, and then they're talking about linear motion. They're being tricky. We're almost done. Number 29, a meter stick of negligible mass. No one ever cares about the mass of my meter stick. Is placed at a fulcrum at the 0.4 meter mark. A lot of numbers here. Okay, 1 kilogram, 0.5 kilogram, 1 meter mark. Definitely got to draw a picture for this guy. Hey, where did those weights? Oh, yes, the weight is equal to mass times g. G is approximated as 10 meters per second squared. And now we get to use torque is equal to R cross F. Torque is equal to the perpendicular force times the radial displacement to the fulcrum, and then we multiply 10 times 0.4, and we multiply 0.6 times 5, and we notice that they're going in opposite directions, so 4 minus 3 is 1 Newton meter. And again, going a little off screen. You guys did so well on this test that it's hard for me to, I got to make it more difficult. They said that the torque about the fulcrum is 1 Newton meter. What about the torque around the center of mass of the meter stick? Well, the torque, fun fact, that's a rigid meter stick, don't you know, is the same everywhere. Here we have the fulcrum pushing up with 15 newtons, 10 plus 5. Net force has to be, we don't want this, that has to be 0. We don't want this thing accelerating up or down. Don't be crazy. That would be crazy. Anyway, calculate for yourself the torque about this point, or the center of mass of the meter stick. It's negligible mass, or this point, or that point, and you'll convince yourself that the answer is always 1. All right, now I know nobody wants to be the person who's the first to put a post in that document where I'm asking you to put a post in the document. That said, put a post in the document.